So these are really meant to be, just written without having to actually
Nói
run
gì
it.
mà close
Also
hết
without
sao?
having to install a default smart
Close
environment.
không có tài liệu.
Waste time using an IDE or something. Just write what you believe would be the program. If there's some kind of typo or whatever, it's no problem. Yeah. Then, let's work on the exercise.
Giờ bài tập là thầy kêu làm cái gì mà ngày mai mới sửa?
Cái code á, cái code không cần chạy gì cũng được, mình viết ra thôi. Tại vì chạy giờ thầy chưa chỉ thì có thể nó mất gì đó.
If the number of partitions is too small, what does that mean? Let's explain.
So we might underutilize
Yeah, exactly. We underutilize the cluster, so we don't have enough partitions. So what will happen to the cluster's performance? Sorry?
sorry?
What will happen to the performance of the cluster?
They will be cluster running very large, and some cluster is not running.
Yeah, we will have very large partitions. So having very large partitions means that it may even happen that the cluster doesn't finish the computation because it may run out of memory because a single node gets just too big a job. So it's a bad idea to have not enough partitions. And also be a problem if we have too many partitions. Very many, like 1 million partitions. So what happens if we have too many partitions? This is a performance problem.
Too much scaling. Too much scaling and increase the software cost.
Yeah, exactly. So we have too many efforts for scheduling and too much overhead. So the overhead will increase up to a point where the cluster is just busy managing itself and not more problem. So of course you have to take care that the granularity you choose for your problem is always adequate and not too coarse and not too fine-grained. And because otherwise, I mean, if you have too many partitions, it cannot really happen that you run into problems like out of memory or something, but it can take to infinity to finish because the overhead is just consuming too many percentage of the overall resources. Yeah, so basically by too few partitions, which means less partitions than threads, for example. If you have less partitions than threads, you always have too few partitions, right? Because yeah, every thread needs to be busy in order to have in order to actually make the cluster work efficiently. Then you have a limited degree of parallelization. Some nodes may finish earlier than others, and in general the granularity is too coarse, you're not doing it efficiently. And yeah, for too many partitions, as you approach too many partitions, the management overhead of course increases. And along with that, the efficiency of the cluster is increasing. So finally, the cluster may be busy with organizing the decomposition of data rather than with solving the problem. So of course, the truth is somewhere in between. And a good guess is take at least as many partitions as we have threads, but usually it's a better idea to have like 2 or 3 times more than that, which is still not a problem. So actually, it's most of the cases it's easier to run into the first problem than the latter because well, Spark is actually quite efficient in managing many partitions. So you don't really have to have a large number of partitions to actually make the overhead count. And even if you have partitions which mean that Spark is only busy with half a second with a single partition, that's still efficient. So it's very difficult to make Spark actually perform in the inefficient range, but of course it's possible, but very often people are underestimating how many partitions are productive. And even then, it's, I mean, you can always try to scale up, right, or scale down. So play with this if you have the impression that it's not working efficiently. You can, for example, double the number of partitions and look how it changes. If you make the partitions too large, so the number of partitions too small, you will notice that at some point you actually probably run out of memory. What do you have to take care of when creating RDDs out of files of the local file system? Not too difficult, right? So what's the problem? Yeah, exactly. So they must exist on the nodes, and if you haven't replicated them before, they don't. So, ensure the files are present on every node, but of course, it's possible to do that, right? So you could have some kind of startup script which prepares it, and for example, uses some kind of network share to copy the file to every node. So yeah, it's possible, but it's not something Spark will take care of. So if you point to a local file system source on Spark, it will just assume the files will be there on every node. And as I said, you don't notice it unless you actually run it on a cluster. What is the difference between importing data via whole text files and text file? What about the first one, whole text files?
Whole text file is like a folder. Our text file in that folder is imported as one dataset. Text file you only get one text file specified as the
yeah, basically. So it creates, whole text files creates one dataset per text file, while text files creates one dataset per line. So yeah. Are there errors which can only occur when running Spark on a cluster and not locally? Yeah, I mean, pretty obviously it was said like it could happen that you are running out of memory, for example, on a cluster. So yes, there are several errors which can occur. Basically, these are errors which result from the parallel processing. They may have been masked in the local execution because there was only one thread. Or it could be errors resulting from the non-availability of resources on all nodes. For example, local files which are not present on every node. So yeah, be aware that even if something is running in parallel on your local machine, it may still fail on the cluster for some reasons which don't have to do anything with the parallelism itself, but with the configuration, right? The availability of resources. Other errors which can only occur when Spark is running locally and not on a cluster. So quite the opposite. Is it possible that we have a problem then? What would you say? So? Yeah, I mean, it's not common, right? So usually the problem is of course the opposite. But it can happen because it's basically like two different configurations, right? You could have a Spark program only be prepared for the cluster environment, and then if you run it locally, which may be an exception because usually you always deploy your clusters and run it, so it may not work with your local configuration. For whatever reason, because there is a resource only available on the cluster, but not on the local machine. So yes, it's possible, but it's not common. Yeah. It's usually not a problem, because usually the workflow is that you first run it on your local machine, and then if it works, you run it on the cluster, not the other way around. It would, it would usually be a waste of resources to actually run something permanently on the cluster. Especially if the cluster is a cloud resource, then you are paying by every executed minute, so this is expensive. Other errors which cannot occur if there is only one thread, but can occur if there are two threads, both on local execution.
Race condition.
Yeah, exactly. So of course all kinds of errors which are related to parallelism itself. So like race conditions. So of course, if you have, you should be aware that your programs will be run in different threads simultaneously. So make sure that you're using the mechanisms you know to ensure thread safety, like locks, and synchronization. Because of course you can have race conditions, and this is not something directly related to Spark or cluster stuff. It's just because of the parallel execution. But as I said, that's the reason why you should always test it with two threads. You won't notice if you have exactly one thread. It will always work with one thread. So based on what has been introduced before, write a Spark program which reads a text file containing a single number in each line. Each number shall be projected to its triple, then from the resulting set, all numbers smaller than 10 shall be removed, and the remaining numbers shall all be added up. The result shall be printed to the console. Does someone want to show the program, maybe? Someone is on the machine. Can show it? Show it to us. Nobody wants to show the program, okay. I mean, it's not complicated, right? Then nobody does. As I said, so the idea was, don't have to run it on the ID right now. Just use the commands we had on the slides before, and basically this is all just configuration stuff to create a context. But the interesting part is here that we create an RDB out of our text file, and then we have the snap operation, which is basically just converting the string into an integer. Then we have another map operation, which is basically just projecting the number to the triple of the number. Then we have a filter statement, which filters out all values which are larger equal to 10. And then we have a reduction step, which basically just adds up all the numbers, and then finally we are getting the string representation out of this. And then we can output it to the console. so not very complicated. Okay, describe the difference between transformations and actions. Which should be understood by now. So who wants to describe it? Yes?
So transformation is like perform some changes in the data. Meanwhile, the actions we have to do some calculation to get a result.
Yeah, exactly. So transformations are just projections, and the projections are just used to create an execution graph. And actions are something, actions are also operations on the data, but they have the property that they require the actual calculation and thereby the execution of the execution graph. So only an action equals to an actual job. So for every action there is a job being run on the cluster. And this job consists of all the transformations which have been defined before and then the action which actually triggers the job. Let me see what I wrote here. So transformations are manipulations of RDBs in the form of mathematical projections which are only used to build an execution graph when they are encountered. Actions require the merging of partial results and therefore trigger the actual one of the cluster. Okay. Why is there caching persisting in Spark? So what would be missing if we didn't have caching persisting in Spark? Who wants to explain? Yes?
Like repeating the same RDB over and over.
Yeah, exactly. So it avoids recomputing RDBs because, as I said, if we have an action, so of course everything is calculated, but then after calculation it's thrown away. So if you want to actually prevent something from being thrown away, we need to cache it or persist it, and then we don't need to do the calculation. But of course there are these different levels for persisting, which we have to be aware of. What do you have to do in order to make local variables available to all cluster nodes? There was a special mechanism for this. Do you remember how it's called? Yeah, exactly. So the special mechanism I meant is the broadcast. So you can use broadcasts in order to distribute them across the cluster. But as I said, it also serialize. Okay, then we have this nice Spark program. Yeah, and also we have this nice definition of, basically it's just calculating the sum of all integers in the iterable. And now the interesting question is, well, first, what does the first section do? Well, what is it creating? What's the output of the, what is chaos?
Each character to value 1.
Exactly. So each character is mapped to the value 1. So not so complicated. But now it gets a little bit more interesting because now we have two other sections and they are probably already guessed out. So they are both doing the same, but they do it in a different way. So what is the result of both sections? I said that they both calculate the very same thing, but they do it in a different way. So what? Exactly. So A1, B2, C3. So so they're grouped. Yeah. So every letter is assigned to the number of its occurrences. But I said it does it in a different way. So you see that section 2 is using reduce by key, while section 3 is using a group by key. So And interesting question here is now, what of the two approaches is more efficient and why? If I say it's not equally efficient, so there's a big difference between them. So what do you think is the more efficient approach to do this? Yeah, do you know? Yeah. Section 2, okay, why?
The second three, it involves two different actions into the entire cluster. For section 2, only involve one action into cluster, is the group by key. For section 3, you need to invoke into the cluster group by key action and then map to the action for you.
Yeah, I mean you're walking the right direction. Yeah, yeah. It will be a bit more precise. So basically, you're right. So section 2 is by far more efficient. Of course, you would notice with this number of model of data, yeah. But if you scale it up, then you will notice. And yeah, the reason for this is that section 2 is first reducing locally and then on the cluster level. And after you have done the local reduction steps, there are fewer data which need to be reduced again. And section 3 is using the group by key, and the group by is creating all the shuffling stuff in the entire cluster, and it's performed on all data. So section 3 is by skipping the local reduction step, but it's reducing globally. And then, of course, it leads to the same result, but we have much more shuffling in the section 3 approach. So it's not, it's actually a very big difference what you're using. Yeah, you see. Yeah, so the difference is here that in section 3, the values are grouped by the graph and then they are transformed to VWeb. So the actual calculation of this web is triggered. So yeah, as I said, section 3 is less efficient than section 2. Yeah, because a part of the required calculations are performed locally on a node. And therefore fewer data must be moved around, so we have fewer shuffling at the lower reduction step, which we both have in both cases, but of course we have less which is still left to reduce. And of course if we have shuffling, we have more network load for the shuffling, and we have also more memory required for the node, because the amounts of data which are treated in the reduction step are larger. So in the worst case, either we need swapping, so actual storage file stuff which really makes things very, very slow, or the drop must be cancelled at all because we run out of memory. So it can actually mean the difference if it's possible or not, the way you're using it. So we're absolutely aware of this, that group by key is dangerous, right? Reduce by key is better than group by key if you have the option to do both. Both into the same result, and always think if you can do a local reduction before a global reduction. Because Spark is not so clever to actually do this optimization for you, because it's basically just doing what you're telling it to do, right? So in this case, you can actually measure that section 3 will take considerably larger amount of time to execute if the input data is large enough. So it's really a big difference here. So and that's because we're skipping the local reduction step. Yeah, so what I wanted you to know is that yeah, even though Spark is capable of doing some kind of optimizations, as I said, like it's optimizing the execution graph, so that's really nice, yeah. That's why we have this requirement of commutativity. But still, you cannot just shut down your brain and do anything. You always have to think what's an efficient way to do something. And that, of course, depends on what you want to do. But if there are several ways to do something, always choose the most efficient one. And that's, of course, always what you can do locally on a node, always do locally on a node. And then, because collecting data from other nodes is always some kind of catastrophe in terms of execution time. Because it will just take bloody ages to get the data there. CPUs are very fast compared to I/O. Yeah, the CPU can things in cycles, and waiting for network traffic can be like millions of cycles until the data is there. So the CPU is, is idling all the time waiting for your data. So network traffic makes your cluster slow in general. So I/O is always slower than CPU power most of the time. So be aware of this. So always try to identify the bottleneck. Yeah, and if the bottleneck is I/O bound, I will also talk later about how to identify the bottleneck. But if the bottleneck is your I/O, then think about how you could solve the problem in a way which requires less I/O. And often that's possible. And the speed gain you can actually get by this is much more than you can get by just hardware optimizations. Okay. Yeah, I guess that's it. All right. So yeah, that's it for today. So just we can quit a little bit earlier than usual. So yeah, thank you all for coming, and I will also upload this very soon, and then we'll meet tomorrow morning again. Thank you.
Lúc đầu là sao rồi đi vẽ xong cái thầy mà thầy là em đây có nhiều sao rồi
luôn. Có được cái cồn chưa? Cái này là khổ của ai được? Và cái màu như của bé chứ. Còn của tôi thì lúc mình mới vô thì không có chìa khóa. Hình như là tôi có hỏi em mới giữ, có hỏi Ngọc rồi nhưng mà không có. Không có hả? Tôi điền đủ hết mà. Tôi lỡ điền đủ hết rồi. Có sửa luôn. Không thì cũng có lại chìa khóa này đi ra ngoài lúc thôi. Ba cái chìa khóa khác nhau. Còn có một cái tiếng lửa. Có không có. Tại tôi nghĩ nó cũng hết rồi.
Ừ.